Hello everyone and welcome back. And today we're finally going to start to talk about some of the rules and techniques that we can use to find the derivative function quickly without having to do this despicable process involving the difference quotient. Now the idea is that almost every situation in the known world can be represented by some combination of power functions, radical functions, exponential, logarithmic, and trig functions. So if we can figure out how to take the derivatives of all of those different varieties of functions, and if we can figure out how to take the derivatives of different combinations of those functions, then in theory we should be able to take the derivative of anything. And we'll be getting started on that today, and we'll be talking about all of those different rules and techniques over the course of the next week or so. So the goal for today is first of all to review how to express quantities like roots and fractions using an exponential format. We'll be using the power rule to find derivatives of functions of the form x to the power n, and we will be using the constant multiple rule to slightly expand the number of derivatives that we can find to functions of the form constant times x to the n. So the power rule is incredibly simple. This is the kind of formula, the kind of theorem that we always dream of in mathematics. So I have a function. The function is x to some power. Here n can be any real number. An example would be x squared, x cubed, x to the power 3/4, x to the power pi, x to some power. If this is your original function and you apply the difference quotient formula, the derivative function will be equal to n times x to the power n minus 1. Now, sometimes you will see this formula represented in a slightly different way. So if you're reading a book or looking at another video, you may also see this written as d dx parenthesis xn equals n times x to the n minus 1. This is exactly the same meaning, it's just expressed in a slightly different way. This is saying that the derivative of x to the n is n times x to the n minus 1. Now let's see a quick example of this rule in action. And let's calculate the derivative of the function f of x equals x cubed. So in this case, the n, as compared to the power rule, the n is 3, the value of that exponent. And so if I want the derivative function, all I have to do is take that 3, take that n value, and multiply it by x to the power 3 minus 1. So in other words, you multiply by the power, and then you decrease the power. And I get 3 times x squared. Full stop, that's it. That is how we can calculate the derivative of power functions like this one. No difference quotient, no giant algebraic mess. Now, you got to be a little bit careful, because this rule can only be applied to functions of this specific format, specifically x to some power. This rule does not work if the base is anything other than just x. So for example, you cannot use this rule if you're working with something like 2x to the power 3. You cannot use this rule if you're working with something like sine of x to the power 2. You cannot use it if you're working with something like x plus 4 to the power 7. And so on and so forth. If you have anything except for x for your base, power rule is not what you need to use. We will be introducing other rules that can be used for situations like this one. Now it may seem that the variety of functions to which the power rule can apply is extremely limited. And true, it is limited, but it's not quite as limited as it might seem at first. I'm going to show you how to express all 6 of the following quantities in the form x to the n, in a format so that power rule could be applied. For example, the constant number 1 can be expressed in this format. 1 is the same thing as x to the power 0. If you raise any non-zero quantity to the power 0, the result of that is 1. Likewise, x by itself can be represented as x to the first power. What about the square root of x? Square roots can be represented by exponents that are fractions. The square root of x is equivalent to x to the power 1/2. And the same thing is true with certain fractions. The reciprocal of x, 1 over x, that's equivalent to x to the power -1. Now the square root was x to the power 1/2. Something like a fifth root would be x to the power 1/5. And if you have taken the reciprocal of a cube root, then that's equivalent to an exponent which is minus for reciprocal, and then 1/3 for that third root. Let's find the derivative of each of the following functions. In the first function, where f of x was constant and equal to 1, was equivalent to x to the power 0. So if I took the derivative of the constant function 1, using the power rule, what would the result be? The result would be take 0, multiply it, and then times x to the power 0 minus 1. But if you multiply 0 by anything, the result is equal to 0. So if f of x is equal to 1, f prime is equal to 0. Now let's take a step back and let's check and see if this conceptually makes sense. The function f of x equals 1 is a constant function, horizontal, flat at the level 1. Because this function is always flat, the derivative of the function is always 0. So conceptually that does make sense. What about f of x equals x, which we know now is equivalent to x to the first power? If you want to find f prime in that situation, we take that power of 1 and multiply it, and then we times that by x to the power 0. Now x to the power 0 is equal to 1, so this is equivalent to 1 times 1, which is simply 1. So if f of x is this linear function, if f of x equals x, then f prime equals 1. Now let's try f of x equals square root of x. The square root is equivalent to x to the power 1/2. So let's apply power rule. Power rule, which says take 1/2 and multiply it. And then take x to the power 1/2 minus 1. If I simplify that expression, now I have 1/2 x to the power negative 1/2. This is totally fine if you wanted to write your answer this way. Alternatively, you could rewrite this and put it back in radical form, 1 divided by 2 square root x, because an exponent of minus 1 over 2 is the same thing as the reciprocal of the square root of x. In the case of 1 over x, this is equal to x to the minus 1. So based on power rule, the derivative would be take minus 1, multiply it, times x to the power negative 1, take away 1. So, slightly simplified, this would be equal to negative x to the minus 2. Or if you wanted to express this slightly differently, you could also say negative 1 divided by x squared. How about the fifth root? I encourage you to pause the video and try to find the derivative of the fifth root on your own. Now that you've tried it, let's rewrite the fifth root as x to the power 1/5. Then f prime would be 1/5 x times 1/5 minus 1, which is negative 4/5. And how about 1 over cube root of x, which is the same thing as x to the power negative 1/3. Then f prime would be negative 1/3 x, and then take negative 1/3 and reduce it by 1, and we get negative 4/3 as the new power. Now let's introduce one more rule to slightly expand the variety of functions whose derivative we can calculate. The constant multiple rule says that if f of x is any function, and you want to find the derivative of not f of x, but of some number times f of x, you can do that by taking the derivative of the function without the constant and then multiplying the constant afterward. So let me show you what I mean here. I want to find the derivative of f of x equals negative 5 times x squared. So I'm trying to find the derivative of a number times x squared. The constant multiple rule says take that minus 5 and set it aside for a second. Worry about it later. First, find the derivative of the function x squared by itself. Now x squared is a power function, and we could apply a power rule. So the derivative of x squared would be bring down the 2 and decrease the exponent from 2 to 1. So after simplifying, the derivative would be equal to negative 10 times x. Now, a word of warning. This rule is not telling you how to find the derivative of a constant function. It's telling you how to find the derivative of a constant multiplied by some other function. So let's take a minute and let's see if we can figure out what the derivative of a constant function would be. What happens if you have f of x equals c? What's f prime in that case? I'm trying to find the derivative of the number c. Now c is the same thing as c times 1. So the constant multiple rule says that you can find the derivative of 1 first and then multiply the result by c. Now recall from a couple of pages ago that the derivative of 1 was equal to 0. If I multiply that 0 by a c, it won't be affected and it will remain 0. So what's the big takeaway? The big takeaway is that derivatives of constant functions, just one number floating out there, are 0. Once again, this makes sense from a conceptual point of view. Constant functions, when you graph them, are always flat. Because constant functions are always flat, the derivative of a constant function is always 0. Let's see if we can notice anything interesting about the derivative of any linear function through the origin. The function of the generic form some number, let's call it m, times x. So I'm going to try and find the derivative of m times x. And the constant multiple rule says that you can set that number m aside for a second and calculate the derivative of x by itself. Now we've calculated the derivative of x before. The derivative of x was equal to 1. So the derivative of a linear function, f of x equals mx, is equal to a constant function, just the number m. Again, let's conceptually check to see whether this is sensible. Really, the defining feature of a linear function was that a linear function changed at a constant rate. So it makes sense that f prime, which represents the rate of change of the function f of x, it makes sense that f prime should be a constant number in this situation. Now suppose that instead of being asked to find the derivative function, f prime of x, you're being asked to find the value of the derivative at a specific location, f prime at a. You need to be a little bit careful when you're asked to do something like that. Because if you're using the derivative rules, you have to do things in a specific order. The first thing that you have to do is find f prime at a general x value, the function f prime at x, using the derivative rules. Only once that is done is it safe to plug in your given a value. So for example, someone gives us the function f of x equals x to the 6th power, and they want us to find the value of the derivative at the location where x is equal to 2. I'm going to show you a wrong way to go about this calculation, and then I'm going to show you the correct way to go about this calculation. The wrong way to go about this calculation is to plug in x equals 2 before taking the derivative. In that case, f of 2 would be equal to 2 to the 6th power, which I think is 64. And then if I was going to try and take the derivative of 64, I would be taking the derivative of a constant, and the derivative of a constant is 0. However, we can check at a glance that this answer is absolutely not correct. Because if we look at a quick sketch of the graph of f of x equals x to the 6th power, we can see that when x is equal to 2, the graph is not flat. That's a sure sign that something has gone wrong. The value of the derivative can only be equal to 0 at a location where the original function was horizontal. If you're getting 0 for the derivative at a location where the original function is not horizontal, something has gone terribly wrong. In this case, the error was to plug in 2 before finding the derivative function. If you're going to find the derivative at a point using the rules, the first thing that you have to do is find f prime at x. So using the power rule on x to the 6th, I'm going to take that 6 and bring it down to the front, and then decrease the power by 1 unit. so 6 comes to the front, and then the 6 becomes a 5, decreased by 1. Only now is it safe to plug 2 into the result of the derivative function. So I get 6 times 2 to the 5th power, which I think is 192. Now let's check if conceptually this checks out. 192 is a positive number. And if I compare that with the graph of f of x equals x to the 6th, the graph is tilted upward, the function is increasing at x equals 2, and therefore it does make sense for us to get a positive derivative. Now something that I really want you to keep in mind over the course of the next several days, as we're learning all of these derivative rules and formulas and techniques, I don't want you to get so caught up in the nitty-gritty of the rules and how to use the rules and when to use the rules that you forget conceptually what the derivative represents. I don't want you to forget that the derivative represents the slope of the tangent line to a function. I don't want you to forget that the derivative is the instantaneous rate of change. I don't want you to forget that the derivative is positive when the original function is increasing, that the derivative is 0 when the original function is flat, that the derivative is negative when the original function is decreasing. I don't want you to forget that the derivative of the position of an object represents its velocity. So let's practice using that conceptual knowledge. Let's find the equation of the tangent line to the function f of x equals square root of x at the location x equals 9. Now remember, if you want to find the equation of the tangent line, you're going to need two things. You're going to need the slope of the tangent line, which is equal to the output of the derivative at the given x value. You're also going to need a point on the line, which is given by x equals 9, and y equals the output of the original function at 9. Now working on the slope, I need to find f prime of 9, which means that I need to first find f prime at x. I need to first find f prime at x so that afterward I can plug 9 into that formula. But we've already calculated the derivative of square root x several pages ago. Several pages ago we found the derivative of square root x was 1 over 2 square root x. Now it's safe to plug 9 into the derivative function, and f prime of 9 is equal to 1 over 2 root 9, which is 1 over 6. Now for the point on the graph, 9 is just 9, so let's figure out what the y value is. What is f of 9? If the function f of x gives us square root x, then the function f of 9 gives us square root 9. So f of 9 is equal to 3. And the point on the line is given by x equals 9, y equals 3. Once we have a point on the line and the slope of the line, we can finish finding the equation that they asked for. Using, for example, point-slope formula, I can say the equation is y minus the y of my point equals the slope, which was 1 over 6, times x minus the x of my point. So in my case, x minus 9. You can leave it like this if you want to. I generally prefer to have y isolated. So I might write something like 1 over 6 x minus 9 plus 3 as the equation of the line tangent to square root of x at x equals 9. As usual, this is something that I'm going to check graphically to make sure that I got an answer that makes sense. Here is the function square root of x, and here is the location on the graph where x is equal to 9, and correspondingly y is equal to root 9, which is 3. So now I'm going to graph the line y equals 1/6 x minus 9 plus 3. And we can see that this pink line that just showed up is truly tangent to the graph of square root x. The pink line also passes through the point 9, 3, and the pink line and the blue curve are tangent. They are almost completely overlapping, close to 9/3. So suppose we're in a situation where we're on the top of some building. And from the top of the building, we decide to drop an object. So as a quick little sketch, here's the building maybe. And here's the object, and I decide to drop it directly off the top of the building, and it falls down. I'm going to measure this object's position at any given time. When I measure the position of an object, remember that we have to manually set and agree upon what position will be the start. And so someone decides, okay, I'm going to decide that the start is at the top of the building. The start will be basically at the object's starting position when I first dropped it. They also have to set a forward direction. And so in this case, they say, well, maybe the most natural thing is to say that forward is going to be up. So as time goes along, the object starts at the starting position and falls downward, which is opposite of the forward direction. So over the course of time, the object is moving away from the forward direction, and the object's position is getting more and more negative. Now, if you agree to set up a problem with this starting position and with this forward direction, you can actually find a function which can be used to predict the position of the object at any given time. If you measure time in seconds, and you measure position using meters, then the object's position at any given time can be represented by the function -4.9 times t squared. It turns out that this is the actual physical function that really in real life could be used to represent the object's position. But there's a tiny catch. The tiny catch is that this function really only works if your object is pretty aerodynamic. So something like a bullet, for example, it would work better for a bullet than it would for something like a feather, where the feather has a lot of air resistance, a lot of drag, and it tends to hover and float. So using this model, let's find the velocity of the falling object after 3 seconds. And let's go ahead and include units in our answer. Remember that the velocity of an object is the derivative of position. In this case, the position is given to me by the function f of t. So if I want the velocity, I need to find the derivative of f of t. Symbolically, it's represented by f prime of t. And in particular, they're looking for the velocity after 3 seconds. So they're looking for f prime at the location where t is exactly 3 units. So the first thing that I'm going to do is I'm going to find the derivative function, which means I'm going to find the derivative of -4.9 times t squared. Now in this case, the input variable is given by t, and so I'm not going to use d over dx to represent the derivative of something. I'm going to use d over dt, because in this case, t is my input variable. So by constant multiple rule, I can ignore negative 4.9 for just a second, and I can find the derivative of the function t squared using power rule. So 2 comes to the front, t squared becomes t to the first power, and I get negative 9.8 times t. Alright, I'm a little short on space here, so let me just write something in the margins. The next thing and the last thing that we would have to do to answer this question is to plug t equals 3 into this formula. So f prime at 3 would be equal to 9.8 times 3, which would be equal to negative 29.4. Now the question is, what would the units be of this velocity? Now we were given the fact that the units of the outputs, the units of the y values were meters, and the units of the inputs of the t values were in seconds. So if I am measuring a rate of change of this function, the units of the rate of change are going to be in meters divided by seconds. We might say this in English, meters per second, which would be a little bit more natural, I think. So this object is moving downward at a rate of negative 29.4 meters per second. That is what's happening with this object at time t equals 3. So now we have in part B some information about how tall this building is. This building is 10 meters above the ground. So roughly speaking, this building is somewhere between 2 and 3 stories high. If you drop this object from a building, which is 10 meters tall, how fast is the object moving when it strikes the ground? Now the big difference between this question and the one in part A is that we're not explicitly given the value of t. In part A, we were asked for the velocity when t was equal to 3. But in part B, we're asked for the velocity at some currently unknown time, whatever time the object hits the ground. So the first thing that I'm going to try and figure out is, based on the given information, what is the value of t? When does the object hit the ground? Now, I have agreed that the starting position, the position which will be called 0, is here at the top of the building. When the object hits the ground and is at the bottom of the building, the position of the object is now going to be at negative 10. Why negative 10? 10 because the building is 10 meters tall. So there's going to be 10 meters between the top of the building and the ground at the base. Negative 10 because someone decided at the beginning of this problem that up was going to be the forward direction, which means that down toward the ground is going to be the negative direction. So when does the object hit the ground? We can now rephrase this. When is the position of the object equal to negative 10? Let's do a quick solve for t. T squared would be equal to negative 10 divided by 4.9, which is about 2.041. And if I solve for t, I get that t is equal to the positive or negative square root of 2.41. 2.041. However, the only thing that I'm going to keep of these two solutions is the positive time. Although occasionally in some situations it makes sense to have negative time, in this case positive time will be used because we're looking at the behavior of the object at some point after it was first dropped. So this would be 1.4 seconds after the object was first dropped. So now that I have the time, if I want the velocity at this time, all I have to do is plug this into the velocity function. So interestingly enough, this turns out to be almost exactly 14. Not exactly 14, but almost exactly 14. So the object, when it hits the ground, in this scenario, where the building is only 10 meters tall, the object will hit the ground at a velocity of negative 14 meters per second. Now, why are these kinds of calculations useful? Now, the velocity of the object when it hits the ground is one of the components that's used in determining the force of the object as it hits the ground. Velocity makes a big difference, and so does the object's mass. If you know the object's mass and how fast it's moving, you know, generally speaking, how much damage it will do when it hits the ground. So this has been used to answer some interesting questions such as, if I dropped a penny from the top of an Empire State Building, would it kill someone if it hit somebody on its way down? Things like that. This can be used to answer that. Okay, that concludes today's material. We introduced the power rule and the constant multiple rule, and we practiced using them on a variety of different functions. In particular, we learned that the derivative of a constant function was equal to 0 at every point. The derivative of a linear function was always equal to just the slope of the line, n. Alright, my USB device is freaking out, so let's end the video here.